Okay, hopefully you guys can hear me. Alright. And actually, take this off. Alright. Give me 1 second, guys. I'm sorry. Hold on. Really quick. Hold on. Okay, sorry about that, guys. Hopefully y'all can hear me well enough. So, let me see here. What I'm gonna do is I'm gonna try to actually move this stuff right here. Hopefully it can... Hopefully it still looks fine. And then, yeah, so just so I can see the chat, if anything. Alright, so, hold on, guys. Okay. Like I said, hopefully y'all can hear me. What we're gonna do in this, live stream is we are going to... Sorry guys, hold on. We're gonna go over section 1.2 of the what is it called? Of the Precalculus textbook by, well, it's by from OpenStax. So, give me 1 second. Sorry guys, hold on. So in the last section, we learned about functions and function notation. And now in this section, we're going to learn more about domain and range. I do believe that I made a video on this. I just never uploaded it because it was just a lot to go over. And I feel like live streams are actually better. And I did make a post on YouTube regarding, you know, live streams in general and how I couldn't do them very often, but I will say that maybe once a week, every Saturday, I can squeeze time in to do one every now and then. So either Saturday or Sunday. So, I'm not really gonna read the introduction here. I mean, I know it's about movies and about, like, The Grudge, The Conjuring, etc., but it just, to kind of summarize what the first part means is we can represent any kind of, any kind of real-life application or real-life data as a graph, where the x-axis is considered our independent variable, y-axis is considered the dependent variable, and similarly for the market share of horror movies by year. So the year is the x-axis, the percentage is the y-axis. That's all that means. So we know that it says in functions and function notation, we were introduced to the concepts of domain and range. In this section, we will practice determining domains and ranges for specific functions. So now we're going to get into actually how to find the domain and range of specific types of functions, whether it be a polynomial, rational, radical, etc. And keep in mind that in determining domains and ranges, we need to consider what is physically possible or meaningful in real-world examples, such as tickets, sales, and year in the horror movie example above. What this means, guys, is that in some cases, when they're giving you application problems, which we will look at them hopefully in this stream, when it comes to domain and range for real-world applications, we cannot have negatives per se. So, like, if I were to say, for every, I don't know, I guess we'll look at some examples once we get there, but the point is that if it doesn't make sense to have a negative value of something in real life, then most likely that's not a valid application, or we wouldn't put the domain as, we wouldn't include negatives in the domain when it comes to the word problem we're given. But we will look more over that in, later in this section, if we get there. So, it says we cannot include any input value that leads us to take an even root of a negative number. So what that means is that when they say that, and actually I forgot to, hold on guys, I'm sorry. Give me 1 second. Let me just, 1 second guys. Hold on. Give me 1 second, everybody. Okay, so, okay, give me 1 second. I'm gonna just do this. Okay, so I'm just gonna name this, and actually, I should have just, I should make a notebook for, I don't think I even did, but what I'm gonna do is I'm just gonna create a notebook. Hopefully, give me a second, guys. I'm sorry. Hold on. One second, everybody. Let me just, Alright, guys. Now, so what it means when they say we can't have a negative number in the domain, or the even root of a negative number, What they're talking about, guys, and I'm just going to quickly explain this, the even root of a negative number. It basically means that we have, for example, the square root of -4. We can't have this. This is not a real number. Does not apply. To real world application. So I just want to make that clear. Anytime we have like negatives, especially this, something like this isn't even a real number, so we cannot even consider that to be in the domain of any function, because it's not a real number, and we will get more into that hopefully once we get into the complex numbers. If they do cover those in this book. But yeah, so if the domain and range consist of real numbers, so it says, for example, we cannot include any input value that leads us to take an even root of a negative number if the domain and range consist of real numbers. So, like I said, if they're supposed to be real numbers, then there shouldn't be a value that is not a real number for domain and range. They must be in the real number system. Or in a function expressed as a formula, we cannot include any input value in the domain that would lead us to divide by 0. What that means, guys, and like I said, that involves rational functions. We will get into that, but just so y'all know, this is just a reminder. And this is something that a lot of students... So I just want to... Let me actually explain the common mistake or the common misconception. / mistake in arithmetic. And actually, I'm sorry guys, hold on. What I'm gonna do, I'm gonna try to, in arithmetic, and what I want to say here is that a over 0 is equal to 0. This is absolutely not true. We cannot do division by 0. Okay, a lot of people make that mistake. It is the most common mistake in algebra. We must remember, guys, it is not allowed in math, in the rules of math. We do not do division by 0. Absolutely not. We have to remember that, because if you keep thinking that we do, give me a second, guys. If you keep thinking that it equals 0, I mean it's wrong. We can say 0 over some value a is equal to 0, but also 0, even 0 over 0, does not equal 0. So this is another misconception. So I just want to make that very clear, guys. I know that I don't have to go over this, but this is really, really, really important to know by now. Now here, we want to remember zero over zero is undefined, and a over zero such that a is any real number is also undefined. We do not know what these are. Now, if you ask me, well, how come 0 times 0 is 0, but 0 over 0 is not 0? To be honest, I don't really know exactly why, but just remember that these are undefined, okay? Any number that we put on the top, we cannot have a 0 at the bottom. If we do, it is undefined. So I just want to make a little review of that. Or any function. And then it says we can visualize the domain as the holding area that contains raw materials for a function machine, and the range as another holding area for the machine's products. So what you put in for A, you get out something for range. So like what you put in for the domain, the function machine kind of works as a little machine, and then it gets out something for the output or the range. Now, it says we can write the domain and range in interval notation. Which uses values within brackets to describe a set of numbers. And actually, let me zoom out. And let me take this off. So, let's see here. In interval notation, we use a square bracket when the set includes the endpoint and a parentheses to indicate that the endpoint is either not included or the interval is unbounded. For example, if a person has $100 to spend, they would need to express the interval that is more than 0 and less than or equal to 100 and write parentheses 0 to 100. We will discuss interval notation in greater detail later. Let's turn our attention to finding the domain of a function whose equation is provided. Oftentimes, finding the domain of such functions involves remembering 3 different forms. First, if the function has no denominator or an odd root, consider whether the domain would be all real numbers. Second, if there is no denominator in the function's equation, exclude values in the domain that force the denominator to be 0. If there is a denominator in the function's equation, exclude values in the domain that force the denominator to be 0. We will go over these things in a minute. Third, if there is an even root, consider excluding values that would make the radicand negative. So these are just in words what they're trying to talk about, but again, I'm gonna explain what those things mean as we go along this section. Now, now it says the smallest term from the interval is written first. The largest form of the term in the interval is written second, following a comma. Parentheses means that you're including it. Parentheses means that you're not including the number in that interval. And brackets means that you're including it. I will say that for negative and positive infinity, because it is unbounded, you will always put parentheses. I just want to add that in there because I don't know if they put that in there. I know they set it up here if it was unbounded, but I'm going to explain this, guys. The thing is that when we read this, of course, it is confusing because you don't know what it means, but once you see it, you'll know what it means, and I will explain it in symbols and math. Now, there is a table here that we're given. The first thing I want to go over is this part here. We say this as x is greater than a. So I'm just gonna like try to I guess in my own words define each of these. So the types of intervals. So here we want to go ahead and look at again we're looking at types of intervals included, you know, that are studied in mathematics, specifically in algebra, and you know, beyond that. One of them is so I want to say a, and actually let me look at the first one here. I want to say this, so it's x greater than some value a, okay? So so here we're gonna go ahead and say that, you know, the way we read this, read as, this is, we read this as x greater than a, or, so this is one way. This is one way we read it, x is greater than a. Or we also say x is greater than a. Okay, so I just wanna, actually, I'm gonna go ahead and just let y'all know what each symbol means. This symbol, so here, when I say this, so the symbol, I just want to kind of go over some review here. So just so we understand what each of these symbols means. This means greater than. So that's one of them. That's greater than. This means, so that's number one. Number two is, this means less than. Okay, guys, that means less than. Okay. And then number three, this means greater than or equal to, and then another one here, which we're gonna go ahead and go over. Number four means the following, and it's gonna be, hold on guys, I'm sorry. Give me a second, everybody, I'm sorry. Number four, we know that this one, so again, I'm just gonna, this here means this here means the following, and it's going to be, and actually, I'm sorry guys, give me a second. It should be like this, less than or equal to. So I just want to make it very clear, guys. I know I don't need to, I don't need to define this, but we want to make sure we understand the symbols when it comes to algebra. We want to understand what all these math symbols mean. If you don't understand them, then it's going to be very difficult. Like I said, all of this stuff is like, it's so important for calculus. So it's kind of like a one final chance. If you are in pre-calculus, it is one final chance to study everything before you finally get into calculus. If you are taking calculus, that is, in the future. Okay. So, like I said, x is greater than a, right? We know that x is greater than a is, we read this as x greater than a, or x is greater than a. We're gonna just go ahead and kind of do this. So when this happens, guys, so the way that I like to say this, and the way I like to put this actually, because this is gonna be, you know, it's gonna help when you're doing these kind of problems. I want to say that maybe, for example, a is equal to 4. So compare two real numbers. A is equal to 4, and then we can say that x is equal to, I don't know, 7. So if I say this, it's really gonna be like saying the following. So it's gonna go, so we know that 7 is greater than 4, right? And the way that we say this, we know that the interval would be from parentheses 4 to 7. Now, I do want to say, guys, I do want to say the following. So if, and I know I don't need to do this, but if x is greater than a, if x is greater than a, some number a, then a is less than x. You have to kind of make that connection, guys, because that's how I did it when it was like from negative infinity to this, etc. I'm only going over this because I know that it can be confusing. And I know that some people just, you know, you have trouble with these. Now, yeah, and like I said, you can compare it to numbers. Pick two numbers that satisfy the a and x value for both of these inequalities. But you just have to understand the definitions of those inequalities, what they mean. Okay. Now, in this case, we know that so one of the things is that greater than is a parentheses, which means, so we use parentheses if we are given a greater than or less than, or positive or negative infinity. right? We always do that. We use parentheses for those, for the open and close parentheses, but, and then we use brackets if we are given less than or equal to or greater than or equal to. So like I said, I just want to state that because it is very important, guys. We need to understand that in order to, like I said, in order to do these kind of problems, we have to understand that. Otherwise, it's going to be very difficult if we don't understand these problems. Sorry, guys, hold on. Hold on, guys, 1 second. Give me a second, everybody. Stream out. Okay. So yeah, as I was saying, that is how we do that. So, let's see here. Hold on, everybody. Let me put this as live chat, and then, okay. So as I was saying, guys, like I said, we use brackets if we are given both of those. We use parentheses for positive or negative infinity, so on and so forth. And I just want to make sure, okay. All right. Now, let's move on to some more terminology here. I'm sorry, guys. Oh my goodness gracious. Okay. So, in other words, if I am saying x is greater than a, well, x greater than a, right? This is my inequality. I'm saying all real numbers x greater than a. So, in other words, the way that I'm gonna say this as an inequality, if you remember from college algebra, this is gonna be, and if you're doing, by the way, if we're doing greater than or less than, this indicates an open circle or hole in the interval. So, or at that x value. So I know that if x is greater than a, well, it's gonna go, so let's say that x is, or let's say that a is over here. This is a, and I'm gonna go to the right. I'm gonna say that they're all the numbers greater than a. So to the right, we're gonna shade to the right, and because it is greater than, we're gonna do a open dot. So it's gonna be like this, and that is how we would graph it. Now, in interval notation, we know that if I keep going forever and ever to the right, it is, you know, here's infinity, so it's gonna be from A, so here's going to be the parentheses at A, and then comma, and then infinity will have the closed parentheses. So remember that infinity always has parentheses regardless, because we're going in order, from, we're going in order with numbers. So it's going to be like this. And we call this, if y'all remember, we call this interval notation. So this is interval notation. So in an interval notation, this is A, comma, infinity. And remember that our inequality was x greater than A. Okay, so these are two different things that we must understand, guys. It is so important for calculus. I know I took a little long on that one. I'm going to go a little faster here. If y'all hear background noise, I do apologize. Now the second one says x less than A. So again, I'm going to do number 2. X less than A. So again, if we want to know what this means this is read as x less than A. In other words, it represents all real numbers x less than A. Oh, and by the way, guys, I forgot to do this. On the number line, this, oops, I don't know why it does that. This part here, actually, I'm gonna make it blue. This part here represents where x will be, whatever x is. It's basically x is between A. It's really to the right of A, that is greater than A. And that's what represents x, whatever that number x would be, that is to the right of a number A. So I'm really trying to explain it as best as I can. Now, for x less than A, it is kind of the opposite. So again, I'm gonna do a number line here, just a random number line. And I'm gonna put A in some random parts. I'm just gonna put it right here. And I want to do all real numbers x that are less than A. So if I know it's less than A, I'm gonna go to the left. So really, and I know that x is less than A. This represents here an open dot or open circle at x equals A. So really, or at A, I'm just going to say at A. An open circle at A, right? And so then we would put the open circle here, and we want to do all the numbers that are less than A. So really, it's going to be shaded to the left. So we're really going to be shading to the left of the number line. And again, instead of positive infinity being on the left, it's going to be negative infinity right here, because we're doing all the numbers, including the negative numbers that are less than A. But I want to make sure we understand that we are not including, when it's an open circle, I forgot to say this, we are not including it in the interval, meaning that it will not be defined at x equals A. So an open circle, I'm trying not to, like, stay on, like, I'm trying really hard not to, how do I say it? Like, not to, say too much about one part. I'm trying to go a little bit faster here. but also trying my best to, explain it as much as possible, but not over-explain it, guys. So, means the number a, the value a, is not included in the interval. And like I said, we're going to go over more examples these are just definitions, guys, but we're going to go over more examples. You'll see how this connects to functions. Okay. So the way we would say this, again, you're going to kind of think about it the way that you would say this in interval notation. Okay, I don't know why it's doing that. Hold on. Sorry, guys. Hold on. One second, everybody. Give me a second. Hold on. Technical difficulties. I'll be back in a minute. I won't mute myself, but I'm gonna turn this off for a second so that I can just reopen it, because for some reason it's acting weird. Alright, go back here. There we go. Okay. Like I said, it would not be included in the interval. So when I do this in interval notation, we're really, in interval notation, this would be written as, and it's going to go, again, parentheses at negative infinity. So I just want to make that clear. It's a parentheses at negative infinity, because remember, I always said that at infinity and negative infinity, we always put parentheses, regardless of, it's always parentheses. And then here at a would be the other, parentheses to a. So again, I want to state that when it's an open circle, it means parentheses, and I don't know if I already said that. I'm sorry, guys, hold on. It's an open circle at x equals a, so I want to state this very quick. So I just want to say parentheses, whether it's open or closed. I put it in quotation marks so that y'all can, so that I can kind of, they're symbols, so actually I'm going to leave it. I'm going to leave it as this. This means, open circle. I'm sorry, yeah, open circle, excuse me. And brackets mean that, and like I said, brackets mean closed circles. So brackets means closed circle / dot / hole, whatever you want to say it. So, or you fill it in, whatever. I just want to make that very clear. And let me just put like this, and then this part is basically this. This is the representation of both. I'm sorry if it's a lot of rambling, guys. I really want to make sure we understand this stuff because I've tutored many people and they don't, you know, they have a hard time with this stuff. So negative infinity to a, that's what that means. Now let me go a little faster. For the next one, it was x greater than or equal to a. So what this means is that, so x greater than or equal to a. So this means that it's gonna go, the number line representation means that this is all real numbers. So again, all real numbers. X greater than or equal to a. Okay, where a is any number. So the graphic representation, or the number line representation, let's say we have a here. We want to do all the numbers greater than or equal to a. So we know that it's going to be a closed dot. Just like I said, it's a closed dot because it's a greater than or equal to. And we're going to do a bracket. So it's going to be bracket. And we know that we're going to shade all the numbers that are greater than or equal to a. So all the numbers here, all to the right. So it's going to be, and here's infinity. And we know that at infinity again, it's always a parentheses. So we know that that is how that's going to go. And I know that this represents the x value, right? So we're just going to do from a to infinity. We're going to go ahead and do that. So it's going to be in interval notation. We're going to have bracket a, and we can write it this way. It doesn't matter if it's color-coded or not. I'm just doing this for those of you that are visual learners. I know I am. So, to infinity. So, really, I mean, you can just say bracket a to infinity. That would be the interval notation of this one. The thing with these is that there's so much, like, there's different ways to say this, or to say all of these. Like, there's just a lot, so I'm trying to not go too slow here. Now, the third, or the next one, I think this was from a to infinity. So now we're gonna do from hold on, guys. Now we're going to do from negative infinity to a, where a is included. So I want to make sure we understand a is included in the interval. So anytime you see a bracket, it means it's included. We are including that interval. Or that number or value in the interval. Now the next one, we're going to do... I think it was what again? Hold on, guys, I'm sorry. I think it was x less than or equal to a, right? Yeah, x less than or equal to a. So I'm just gonna do the next one, x less than or equal to a. So again, we read this as x less than or equal to a, whatever a is. So I just want to state that really quick. And then we know that if that is true, then on the number line, we're going to have something like this. It's going to go, so let me put A here. And we know that because it is a less than or equal to, we know because this is going on, it's going to be a closed dot. So we're going to put a closed dot here at A. Hopefully it lets me. And then we're going to shade all the numbers that are less than or equal to that. So it's going to be shading to the left, just like that song. So we know that here is the representation of x, whatever the x is, basically meaning that it's whatever number less than or equal to a. And we know that in interval notation, we're going to have, so again, it's going to be parentheses at negative infinity because, again, always parentheses with negative or positive infinity, comma, and then we're going to go all the way to A, and A is where we have a closed bracket, or a closed A bracket instead. So we're going to put a bracket at A because it's a closed dot. We have to remember these guys. These are just, I mean, it takes time, but just remember the terminology. Now the next one is interesting. So now we have another value, a to b. So now the next one, I want to say that this is, I don't even know what number this is anymore. This was number 3. And then this was number 4. So now we're going to do number 5, which is the 5th one. Number 5 says that it's going to be the following. So it's going to go, I'm sorry, hold on. A less than x less than b. So, and again, I'm just going to state how you read it. I'm going to say it this way. Hold on, guys. I'll say it this way. So this is read as A less than x less than b. And or we also say A is less than x, which is less than b. Or we also say it as all real numbers x, between a and b. I mean, there's many ways to say this. Honestly, it doesn't matter as much as long as you understand what it means. It just means, as long as we remember what it means, it just means all real numbers between the intervals or the values a and b. I'm trying not to be so wordy with this. We just have to understand the basic idea of this. We can say it any way we want, as long as, you know, there's many ways to say this, but it's just all real numbers x between a and b. So the way that we're looking at this, here, and on the number line, let's say we have some, again, we have 2 values this time. It's going to be from a to b. So it's going to be like this, and then it's going to go, I'm going to do this. So, and actually, I'm sorry, no. I'm going to do this. Now, it's all real numbers x, you know, a is less than x less than b. So it's between a and b. So we know that, again, if we have a less than, it's going to be an open circle at A. So here is the open circle at x equals A because it's less than. And then at B, it is also an open circle. So really, we want to shade all the numbers that are between A and B. And so the way that we would say this in interval notation is it's going to be bracket and then, I'm sorry, excuse me, it's going to be parentheses at A and then I'm sorry, hold on, and then parentheses at B. So it's going to go like this, parentheses A, comma, B, close parentheses. So we must remember that for calculus, guys. It's very important. So that would be the interval notation. So in other words, just A, comma, B. I don't think set builder notation is as important. It is, I mean, it is mentioned, but if they do mention it in the book, I will go over it. All right, the next one. Now the next one is, I'm going to say this is which one? Number 6. So, this one, we're going to do A less than or equal to X. I think it was, what was it? A less than or equal to X less than B. So now we're going to do A less than or equal to X less than B. I think it's what it was. So this represents, so I just want to, I'm just going to highlight this part. This represents a bracket. And then, so this will represent a bracket. And then this one is going to represent the closed bracket. So we're just going to say that on the number line, I'm trying to do this a little faster. We have, here's A, and then here is B. We're going to put all the numbers between A and B. So this means all real numbers, X, and I'll say it this way, X, between A and B, including A and B. Including A and B. So we're just going to go ahead and put, I'm sorry, excuse me, including A, but not B, excuse me, but not including B. But not including, oh dear God. B. So, we're going to put a closed dot here. Okay. That represents this part. And then we're going to put an open dot at B. So it's going to be like this. And we're going to put all the real numbers that are between A and B where it's, you know, A is included but not B. So we know that if A is included, it's a bracket. And if B is not included, it's going to be a parentheses. So really the interval, so in interval notation, and again, the blue squiggly line represents my X values between A and B. So it's going to be an interval notation. It's going to be bracket, and actually I'm just going to do it this way. It's going to be bracket A, comma, B, close parentheses. Give me a second. So that's number 6. So that is how we say that in interval notation. Now, the next one, number 7, this one is going to be a less than, I'm going to do a, and actually, oh my goodness gracious. I'm sorry guys, hold on. I'm going to just go over these just here. So, this part here, we're going to go ahead and just, you know, it is, this next part just basically means the opposite. It's a less than x less than or equal to b, and it's parentheses a comma b close bracket, because there's less than or equal to, x less than or equal to b represents close parentheses at b, a less than x represents open parentheses at a. Alright, and then the last one just means that if they both have the less than or equal to between a and b, then you do brackets at both sides, and you do filled in dots at on both sides. Now we're going to go over some examples, and I am actually going to, go ahead and, so I'm going to do this first one, and we want to go ahead, and state this as a set, as a set. So our problem says the following, and we're going to go ahead and write this down. I'm going to do it, so this is example 1. Let me just kind of, and what I'm going to do, 210, 310, 420. Give me a second, guys. 530, 640. Hold on, guys. So, what it says here is the following. We want to go ahead and state the domain as a in set notation. So let me write that down here. Okay. I mean, I understand it. I just wanted to make sure. So we want to remember that the domain represents our x coordinate slash x-axis slash x value. Whatever, right? So in our domain, we know that as a set, we have these things going on here. 2, 3, 4, 5, and 6. So in set notation, the domain as a set would be the following, and it would go 2, 3, 4, 5, and 6. So this would be our answer as a set. Okay, guys? That is how we find the domain as a set. I will say if you want to go ahead and try the next one on your own, here it is. It's just, you know, it's the same idea. Now, we're going to want to go ahead and go over example 2. Now, for example 2, it says finding the domain of a function. So example 2 says find the domain of the function. Hold on. So find the domain of the function. And this says the following. So f of x equals, and what was it again? Hold on. X squared minus 1. Now, the main idea here, guys, is that we need to see if there are any restrictions at all. And if there isn't any restrictions, or if there aren't any restrictions, then the domain will be all real numbers. So, I don't really know exactly how they're putting this here. Okay, in interval notation. So, we know that from algebra, this is considered a polynomial function. So, f of x is a polynomial function. Specifically a quadratic function. With degree 2. Okay. And here we want to go ahead and say the following. So we know that, like I said, it's a polynomial function of degree 2. Remember that for any polynomial function, the domain is always all real numbers. So for any polynomial function, where n is any real number, such that n is not a fraction, meaning that if we don't have like x to the 1/3 or whatever, I just want to say, and actually maybe this is not the best definition, basically where we have ax to the n plus something something something, so like we know that for any polynomial function, the domain is all real numbers. In other words, it is from negative infinity to infinity. There are some exceptions to this, and that is when you're doing like x to the 1/2, x to the negative 1/3, so on and so forth. But those are more related towards like radical functions, which we will go over later. Now, some examples of where domain is not all real numbers. So if given x to the n, where n is less than 0 or n is of the form a over b, where I don't know, I'm thinking where a is less than b, then this is not a polynomial function. I know this sounds really confusing, guys. What I am trying to say here is that you cannot, like, the domain would not be all real numbers if you had, like, x to the 1/2, x to the 3/7 or something, or 3/8, dot dot dot, or x to the -2/3. Like, even this, you would not, these are not considered polynomial functions. At least I don't think. And I just want to make sure, actually, I'm sorry guys, hold on. I just want to make sure that my intuition on this is correct. I'm pretty sure I'm right, but I just want to make sure that I'm not giving you wrong information. So yeah, anytime it's like a fraction, where the exponent is a fraction, these are not considered polynomials. They're more likely radicals, or rational expressions, or expressions with rational exponents. So we wouldn't say that the domain is all real numbers for those. I just want to make that very clear. So like I said, with x squared minus 1, because it is a quadratic, we would consider that to be the domain to be all real numbers. And if y'all can want to see, it is -infinity to infinity. Now we want to go ahead and do the next one, where now we are given one that has, you know, it's like a fractional one, and we are given something in the denominator where an x is both in the numerator and denominator. What we call this, guys, and example 4, and what example is this again? I'm sorry, example 3 represents a, and I'm gonna just put this in here, rational function. So a rational function, guys, if y'all don't remember, a rational function is of the form, sometimes it can be of the form with linear factors on top and bottom. Is really of the form, it's like ax plus b over cx plus d, where the denominator cannot be 0, where cx plus d is not equal to 0. What I mean by this, and the reason why I say not equal to 0, is because, again, division by 0 is not possible. If we look at example 3, we are given the following, and it says f of x equals x plus 1 over 2 minus x. So, remember that if we are given a function such as this one, we know that the domain is all real numbers. In general form, the domain is all real numbers such that cx plus d is not equal to 0. In other words, if I were to go ahead and do this one, basically the denominator cannot be 0. I would say this in terms of words. I would say that the domain is all real numbers such that 2 minus x is not equal to 0. Now, in other words, if I were to solve for x in this part, so if I were to solve for x here, I would simply say that the domain is all real numbers. And if I do that, I'm going to do it separately over here. I'm going to add x to both sides of this equation here. I mean, it's a not equal to, but this expression, this equation, whatever you want to call it, would be 2 is not equal to x, or x is not equal to 2. So I just want to, and it's going to be such that, this means such that x is not equal to 2. In other words, the domain is all real numbers such that x is not equal to 2. I just circled it, but you don't have to circle it like I did. Oh god. Okay. Now, in interval notation, and this is where the union symbol comes in, guys. If y'all remember the union symbol, it is really important for these. We use it so much in calculus. This is what we call a union symbol. Which means we unite, like it's a union between two numbers in one interval. Or between a union of two intervals, basically. So in interval notation, we know that it's all real numbers such that x cannot equal to 2. So I know that if I were to draw a number line, and I say that it's x is an element of all real numbers such that x does not equal to 2. And I know that this is my domain. We would go to 2, put 2 anywhere, and this would help. I mean, you don't have to do this, but it helps if you don't understand how to put this in interval notation. You would put 2 here, and you want to make sure you put an open dot because it is not defined there, but it's gonna go, you're basically gonna shade between to the left of 2 and then to the right of 2. So in other words, what this is gonna be, here's negative infinity and here's positive infinity. This is gonna go from negative infinity to 2. And then we want to put a closed parentheses there, and then union, because it's really a union, and we're going to continue from 2 to infinity. Okay, guys? It is very difficult to understand this stuff. You just want to understand what a union means, the terminology of what it actually is saying. It basically means that you're taking two intervals, kind of, and you're bringing them together for one domain or range. So that would be the domain for that one. And if we look in very carefully, we know that x cannot be equal to 2, right? As it says here, we want to exclude 2 from the domain, and it's all real numbers where x is either less than 2 or greater than 2. It's, but it's not equal to 2 at all. So it would be negative infinity to 2 union 2 to infinity. This is actually a better representation of this. When you have an or means union. I believe so. It means a union. So hopefully this makes more sense. Now, let's move on. Now we want to do the domain of an actual root, or an actual with an even root. The thing with these guys is that, as you can remember from earlier, we had said that when it comes to radicals, we don't like, we don't want it to have a negative on the inside. So this is example number, let me see, hold on, 4. And it says, find the domain of the radical function. And it gives us f of x is equal to, and it's the square root of 7 minus x. Right. Now, now here, we're going to go ahead and look at this one. So, for this one, if given f of x is equal to the square root of x minus h, then the domain is going to be all real numbers such that the square root of x minus h is greater than or equal to 0. There's a reason for this, and it's because we cannot have a negative in the square root. Anytime they tell you to find the domain of a square root function, or this kind of where it's a square root, you must make it greater than or equal to 0 and solve for x. Once you do that, you have to put it in interval notation. Okay? We cannot forget to do this. This is really important to find the domain of a radical function where the degree is even. So for this example, we want to go ahead and do set a square root of 7 minus x. And number 1, set square root of 7 minus x greater than or equal to 0 and solve for x. So we're going to do that. So I have the following. The square root of 7 minus x is greater than or equal to 0. And so to solve for x, we're going to square both sides. We want to remember that to get rid of a square root, we square it. So we have 7 minus x greater than or equal to 0. We're going to add x to both sides. And 7 is going to be greater than or equal to x. So what this means, guys, is that, again, if a is greater than or equal to b, then b is less than or equal to a. This means that x is less than or equal to 7. So my domain is x such that x is less than or equal to 7. This would be in like set builder notation, but in interval notation, well, if you think about how to graph x is less than or equal to 7, I mean, if you draw the number line, the actual number line, and again, you don't have to do this, but it helps if you don't understand how to do it in interval notation. We're going to put 7, and we're going to put a closed dot here, and we're basically saying all real numbers less than or equal to 7. So in other words, we're going to go ahead and just do from negative infinity. So here's negative infinity, here's 7. We're going to put a parentheses at negative infinity, a bracket at 7, and just shade all the real numbers that are between negative infinity and 7. So we're just going to shade, all of this. And actually, like that. So in other words, in interval notation, the domain is parentheses negative infinity to 7, bracket. The range is something else. I don't think we're going to go over that yet. But as you can see, it is from negative infinity to 7. So it's exactly how we did it here. I just want to keep in mind, guys, that the way that they're doing it on this book is not going to be exactly how I do it. So I'm kind of showing y'all my way of doing it, and then the book's way of doing it, and kind of explaining, both ways. But I do want to mention that not every problem that I do in this book is going to be the exact work as my work shown. Now, this is where set builder notation comes in. So, I mean, obviously, we already went over interval notation. I'm not really going to spend too much time with this. Set builder notation is really what I was referring to when we had done, when we were doing domain and range. You can represent that in set builder notation, but only if they ask you to do so. I don't know, to be honest, if on a test they'll allow you to put it in set builder, unless they ask you in an exam, to put state the domain and range in set builder notation. I've hardly used set builder notation from my in my own experience. Mostly they'll ask you to put it in interval notation, but it's still good to know, right? It basically means that you're gonna put a brace, like an open brace, and the X, and then put the line, and then put the interval that they're giving you. That's all that means. So I'm not really going to spend a lot of time with that. And this expression here just means all real numbers. That's really what that means. That little R symbol with the two lines at R, the two, kind of like that. I'm not really going to spend a lot of time explaining what this means. In fact, it is difficult to explain. I've honestly never seen it this way. But this would look like a union. So yeah, set builder notation, it says set builder notation is a method of specifying a set of elements to satisfy a certain condition. It takes the form X such that, or the set of X such that, and then whatever statement is said about X. So, which is read as the set of all x such that the statement about x is true. For example, x such that 4 is less than x is less than or equal to 12. Interval notation is a way of describing sets that include all real numbers between a lower limit and a lower limit that may or may not be included and an upper limit that may or may not be included. All that means, guys, is what we just did. I mean, honestly, the way they're explaining this, in my opinion, is very, it sounds very confusing. It just means, like, if it's parentheses, we are including it. If it's bracket, if it's parentheses, we are not including it. And if it's bracket, we are including it. So I'm just not really gonna go over that much. Now, they do give us here a graph, and we want to specify this example, and this is example 5 from this section, and I'm gonna just type it here. So, example 5 says the following. I'm gonna just put it. And it gives us, like, to put it, describe the intervals of values shown in figure 6. Using inequality notation, set builder notation, and interval notation. And the one that they're giving us, guys, is this one. So I'm just gonna the intervals of values. Okay. So, like I said, we're gonna go ahead and give me a second here. What I'm gonna do is snip and sketch so that I don't have to. I'm just gonna go ahead and do this really quick. And then just try my best to not make it so big, because I know when I paste it here, it makes it really big. Give me a second, guys. All right. Sorry, guys. Hold on. I don't want to make it so big either. I'm trying not to make it really big. Big enough to read, but not to the point that it's like, oh my goodness. So I'm gonna go over this. Here, we are given an expression, or no, I'm sorry, not an expression, a number line, and it's asking us to put it in inequality notation, set builder notation, and interval notation. Now, okay, so I'm with set builder notation. I do believe it's going to be an or symbol, or an or kind of thing statement. So the way that this is gonna be. So first I'm gonna use inequality notation. And actually, let me just look at the solution, because I'm not 100% sure. Okay, I got it. Yeah, I didn't know if that was the way that. Oops, I didn't know if that was the way that they were doing this. I'm sorry, guys. I minimized this on accident. supposed to be over here. Okay. My bad. Like I was saying, I don't know if this is, so I just wanted to make sure of, you know, this stuff here. Alright, so, we want to do this in inequality notation. The way we're going to do this is we're going to go ahead and say it the following way. So here is one part. The way we're going to say that is 1 is less than or equal to x is less than or equal to 3. This is my inequality. Okay, guys. And then in interval notation, or in set builder notation, oh, I'm sorry, and actually, I'm sorry. So it was, this is for this part, and then this part here defines 5 less than x, which is less than or equal to infinity. Or I'm sorry, wait, no. I'm sorry, no. Excuse me. It's gonna be, I'm sorry, no, that's not how you say it. It's gonna be x greater than 5. I'm sorry, guys. And actually, I'm pretty sure that's how they say it. Hold on. Yeah. So that would be the inequality of this. Okay, guys? We have to understand that you have to use that or word when you're doing unions. Now, in set builder notation, or I don't know which one was next. Yeah, set builder notation. We're going to do the following. So it's going to be it is going to be x such that 1 is less than or equal to x is less than or equal to 3, or x is greater than 5. I think that's how you say it. Give me a second. Sometimes they use the line. Sometimes they'll use the semicolon. It really depends. I don't think I really use the line, but you can say it however works for you. I've seen both of them used, like either or. And then finally in interval notation. Well, because they are two different intervals and they're being put together, we would say bracket 1 to 3, bracket, and then union, and then 5 to infinity. And it would be a parentheses on both sides. So I just want to reiterate that this is how we would say it this way, and then this is how we would say it this way. Okay. What's next here? Now, here, we want to be able to know how to find domain and range from a graph. So this is where it is a little more difficult. We're gonna just go ahead and go over this example, and I'm just gonna like copy and paste it because I don't want to draw the graph. But give me 1 second, guys. And I'm gonna say it in interval notation, guys. I'm not gonna say it in set builder or anything like that. Like I said, interval notation I think is the most commonly used type when it comes to these problems. Because I mean I should know because I've taken all the way to Cal 3, so I don't really think we've used set builder as much, but it is good to know it. Either way, because I think they do test you on it if they do want it in set builder. Alright, so this one, we want to find the interval, or the domain and range from an actual graph. So here's how I do it. I always say, so there are 4 questions I want to ask myself. Number 1, 4 questions to ask yourself for these problems. Number 1, what is the lowest x value I reach? Is this x value defined? Number 2, what is the highest x value I reach? Is this x value defined? So this part would be for the domain. And I don't know why it's not responding again. Oh dear God. Give it a second, guys. I'm sorry. I'm gonna just... Hold on, guys. I'm sorry. I'm sorry, guys. Hold on. Give me a second, guys. I'm sorry. 1 second, everybody. One second, everybody. I'm sorry. 1 second. I don't know why it's doing this right now. Okay, guys, sorry about that. I don't know why I was acting really stupid. Oh my dear God. Okay. Alright. Where were we? So, for number 2, you want to ask yourself, again, give me a second, guys. I'll explain in a minute what this means. So, here we're gonna do... And actually, it's going to be what is the highest x value I reach. Is this x value defined? I really don't know why it's doing this right now. Seriously. Give me a second, everybody. Technical difficulties. Oh my goodness. Give me 1 second, everybody. Why is this happening? One second, guys. Okay, I don't even know why it's saying this, but whatever. I don't understand why it's doing that, but I think it looks fine. So I'm sorry, guys. Let me just put it here. And then, okay. I'm sorry, guys. Technical difficulties. So, what is the lowest y value I reach? I'm sorry. I'm going to just say, what is the highest x value I reach? Is this x value defined? So, for this part, well, yeah, like I said, and then number 3, I'm going to say, what is the lowest y value I reach? Is this y value defined? And then similarly for the like we said before, and then what is the highest y value I reach? Is this y value defined? If y'all hear an airplane in the background, I apologize. So we're going to go over this example. So this says the following. So we have some kind of curve here, and you want to again look at where is the curve undefined, where is it defined. So we can clearly say that in terms of the x-axis, there is an open circle here at -3. And so we know that x cannot be -3 because it's an open circle, it's undefined. And then at x equals 1, we know that it is defined there. So I know that over here, x equals 1. So if you think about it from in terms of kind of a number line here, we can clearly see that the lowest x value is -3, but x cannot be -3. And the highest x value is, again, at x equals 1. And x is equal to 1. So we know that in interval notation, or actually, I'm sorry, we know that the domain, because again, I don't have to keep saying interval notation, but I'm going to just say that the domain, and you know, it's automatically an interval notation that we stated in, so we know that the domain is going to be it's going to be parentheses -3 to 1 bracket. So that would be the interval, or that would be the domain of this curve, of this function, right? I would say it's a piecewise because there's restrictions. Now the range, so the range is a little bit harder. Again, so we got rid of the domain. That was that first part, the highest and lowest x value. Now the highest y value, so actually, I'm sorry, for the range, the highest, or, Lord, the lowest y value is going to be at at 0, because this point is -30. I'm sorry, excuse me, no. The lowest y value, actually, you want to see in terms of the y-axis. what is the lowest y value on the curve? Look very, very carefully, guys. If I'm going down, 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 what is the lowest one we reach? It is -4, right? We can clearly see that the graph in terms of y does not go below -4. So we know that the lowest y value is at y equals -4. However, and actually, this one is a little tricky, actually. Let me see the solution. Okay, yeah. So this is a little tricky, guys, and I do think, and I've, like me personally, I have been tricked before by this one, or by these kind. Here, we know that the lowest y value is at -4, and we know that although what I'm actually going to say here is that the highest y value is at y equals 0, because it doesn't go any higher than that in terms of the y-axis. But so the highest y value is y equals 0. I do want to note, although y is not defined at x equals, and I want to say at x equals, it was at x equals, I forgot, at x equals, at x equals 0, I'm sorry, at x equals -3, it is defined at x equals, what was it? At x equals 0. Thus, highest y value is y equals 0, and it is defined. So I just want to make that very clear, guys. This is tricky. Tricky, tricky, tricky. I was tricked almost with this kind of problem, and it was in Precalculus. Hold on, guys. So, all in all, with the range, guys, we know that the lowest y value is at -4. So in interval notation, the range is bracket -4 to 0, close bracket. We're not really going to go over these examples. I mean, I can, but because I already said domain and range is, you know, in terms of like, you have to apply it to real world applications. If it's negative, then obviously it can't be included. Now this is what we call a constant function. This is obviously, and I'm just gonna like quickly go over these. This line, when it's a horizontal line, it is called a constant function. The range, it's really just at y = c. We don't really, I mean, honestly, we don't, it's just c. I don't know why they would put it at bracket c, comma c. I've never seen it that way. For linear functions, it is -infinity to infinity for both. And this is called an identity function, y = x. This is an absolute value function, guys. For an absolute value function, the domain, as you can clearly see, it goes on the horizontal x-axis. We can put anything for the absolute value of x. But for the range, it is only going from 0 to infinity because it's going from 0 upwards. So we can clearly see that the range would be from 0 to infinity. You really have to be careful with the y-axis. That's always the more tricky one. It is the same thing for the quadratic function, y = x squared. This is, you know, it's a parabola, and we can clearly see that the lowest in terms of y that it goes to, it's at 0, and it goes upwards. So what I mean by upwards, it goes to infinity. And the domain is all real numbers, because again, the way that we know domain is that it doesn't have a restriction, whether it has a restriction or not. For a cubic function, this is what I was talking about. If the degree is odd, most likely the domain and range are going to be -infinity to infinity. So, I mean, yeah, this is for all odd functions, or all functions with an odd degree. Odd functions are a different thing. But yes, this is how we would, you know, this for a cubic function, the domain is -infinity to infinity. For a rational function, or reciprocal function in this case, this would be where, kind of like I said, algebraically, you would not include whatever's at the bottom. So in this case, we would set x not equal to 0. And in interval notation, we would say from -infinity to 0, union 0 to infinity. As well as for the range. For the range, this involves a horizontal asymptote. Because the horizontal asymptote is y = 0, we would not include 0 in the range. I will go more over that later, though. For a reciprocal squared function, again, it is that idea that you set the x squared part not equal to 0, and you find the domain for that. So we know that the domain is from -infinity to 0, where 0 is not included, and then union 0 to infinity. We must exclude 0 from the domain, right? And then the range as well. But in a graph, obviously, since they're giving us the graph, we can clearly see the domain and range very clearly. Now, when it comes to algebraically, that is where we have to understand the idea of how asymptotes play a role in domain and range, which we'll get to later. For the square root function, f of x equals square root of x, we cannot take the square root of a negative real number. So like I said, if we cannot take the square root of a negative real number, we cannot put negatives. We cannot include negative numbers in the domain or the range. Even if I were to, like, for example, if I were to say that -3 is equal to the square root of x, well, honestly, I mean, I can solve this. However, I want to strictly say that x is greater than or equal to 0. So, honestly, I mean, if I were to state this, yes, x would be equal to 9. But honestly, we want to, we're only saying that it's for all positive numbers, not for negative numbers. So you have to be careful. I know that the square root of 9 is 3. We are not talking about this is a radical equation. And I'm saying strictly that x is greater than or equal to 0. So I am not going to do like a quadratic equation where I'm doing that plus or minus stuff. That does not apply here. That is if we're talking about like, if we are talking about positive numbers. In this case, to be honest, this would not have a an answer. At least I don't think it would, because if you were to graph it, it wouldn't really have a real answer. I mean, at -3, if you look right here, it is not defined here, so we can't say that. We can't solve that for x. The range, so it says we cannot take the square root of a negative real number, so the domain must be 0 or greater. The range also excludes negative numbers because the square root of a positive number x is defined to be positive, even though the square of a negative number also gives us x. So that's what I'm talking about. You have to really look at the sign for these on the radical. Now this is what we call a cubed root function. This is where this is kind of the only function where if we have a, we can actually find the inverse of if the degree is odd. So I will go more over that later. But this is one where the domain and range is -infinity to infinity because it's all real numbers for both the x and y axis. And this is the graphical representation. So as you can see, we don't really have any restrictions here. Now, when it comes to this, we want to simply state the idea that for any, like I said, for any polynomial function, the domain and range will be defined. For any polynomial function, it's going to be -infinity to infinity. That is all that example 8 is saying. There are no restrictions. The domain and range will be defined for both. Or will be -infinity to infinity, or all real numbers. Example 9 states that kind of problem where we have like, the domain and range of 2 over x plus 1. So this is interesting. We know that if this is true for the domain, we will not include, we will exclude 0 so if, I want to just say this really quick. If given f of x equals some function a over x such that x cannot be equal to 0, And if domain is x such that x is not equal to 0 or negative infinity to 0 union 0 to infinity, then if x is not equal to 0, then for the range, oh my god, why does it always do this? Okay. Jesus Christ. Okay, then similarly, for the range, because x cannot be equal to 0, y cannot be equal to 0. Thus, range is negative infinity to 0, union 0 to infinity. I believe that is all that is saying, guys. Like I said, I'm going really fast with this, guys, because this is not like college algebra. I mean, we learned this in college algebra, so we're not really going to go over it in a lot of detail. So, like, it's kind of what I was saying here. The domain for the domain is always very easy to find. The range is a little harder. I will say that the way that I do it is by vertical and horizontal asymptotes. The vertical and horizontal asymptotes help a lot with doing this, but this is an interesting way of seeing it. But usually, I've never been shown this method, or not before. Typically I've never seen it solved like this before. But the way that I usually do it, and I'm going to explain to you guys, you usually say that if I have f of x equal 2 over x plus 1, I know that my vertical asymptote is x plus 1 equals 0, is equal to 0. Or rather, my domain, I'm just going to say this. Or, no, I'm going to use vertical asymptotes and horizontal asymptotes. So my vertical asymptote is x plus 1 equals 0. We know that the domain cannot be defined at an asymptote. So my domain is all real numbers such that x does not equal to negative 1. And so in interval notation, it'd be from negative infinity to negative 1, union negative 1 to infinity. Now, in terms of the range, I do want to define this very quickly. Hold on, guys, I'm sorry. For the range, the horizontal asymptote, so ax to the n to the m over bx to the n. I'm sorry, guys. Over bx to the n oh my goodness gracious. If let me think. If m is less than n, the horizontal asymptote is y equals 0. So the range would be from negative infinity to 0, union 0 to infinity. That's all I was going to say. I'm sorry, guys. I don't know why. I mean, to be honest, I mean, because again, we excluded, you know, because it can never be 0, then the range would be from negative infinity to 0, union 0 to infinity. But again, personally, I don't like that definition. I do think that that's kind of why I did it my own way. The domain and range of f of x equals 2 square root of x plus 4. Now this one's a little hard. So this kind of has to do with the idea of inverse functions, or finding the inverse. It is a little tricky. So I'm going to go ahead and do it one way. Y equals 2 square root of x plus 4. The easy part is finding the domain, which is no problem. I'm going to say that 2 square root of x plus 4 has to be greater than or equal to 0 for the domain. So divide by 2 on both sides. We get the square root of x plus 4 is greater than or equal to 0. We're going to go ahead and square both sides. Oh my god. Okay. I'm sorry, guys. I don't know why it keeps doing this. So then it's going to be x plus 4 greater than or equal to 0. We get minus 4 on both sides. And we know it's going to be x greater than or equal to negative 4. So the domain would be from it's going to be from bracket negative 4 to infinity. Now, for the range, or I'm sorry, the domain is going to be from negative 4 to infinity. The range is a little bit more difficult. Sorry, guys. So let me think here. Yeah, the range is harder. I'll try to see if I can explain this one. What I'm gonna do actually is I'm gonna use the idea of inverses. So if I let x equal to square root of y plus 4, I'm gonna go ahead and just do the inverse, but I know that, oh, this is tricky. Y has to be greater than or equal to negative 4. In this case, I believe. So I'm just gonna solve for x. I'm sorry. Oh. Hold on. I'm sorry, I'm gonna solve for y, excuse me. And we're gonna go ahead and divide by 2 on both sides here. So then we're gonna get 1/2 x equals square root of y plus 4. square both sides, we're going to get 1/4 x squared equals y plus 4. Okay, guys, and then oh my goodness. And then we're going to subtract 4 on both sides. So it's going to be 1/4 x squared minus 4. I don't know how I'm still writing on this, and yet it honestly, I don't know why it keeps freezing. Oh, Jesus Christ. Okay. 1 second, guys. I'm gonna just... I'm sorry, guys. Oh my goodness. This is annoying. Okay, like I was saying, subtract 4 on both sides. 1/4 x squared minus 4 equals y. But we know that if we have that, I think it was, what was it? Y greater than or equal to -4. So really, give me a second, guys. This is a tricky one. It really is. So I know that the domain is from -4 to infinity, but the range is always the one that always gets me here. It is an interesting one. Let me think about it, guys. I'm sorry. It is a hard one. If I do x greater than or equal to -4, one half x squared minus 4. Hold on, guys. Wow. This is difficult. Yeah. So, let me think here. I wonder if I can do... I have to kind of use my math skills here, guys. If I do this... Oh, no. If I do that, and then I say y squared over 4 equals x plus 4, y squared over 4 equals... or minus 4 is equal to x. I really don't know, guys. This is really tricky. I'm stumped. I'm wondering how it's true for this one. how the range is, let's look at the solution. So we then find the range. We know that f of -4 is 0, and the function value increases as x. Okay. I see. So I guess for the range, it's more like, I see how they did it. So basically, guys, you have to look at the behavior of the graph at x equals -4, and then see from there whether it increases or decreases. So the way they did this, no wonder. So just forget all of this. I don't want to algebraically do it because I feel like it's a lot harder. And I do apologize, guys. For the range, it's different. The range is very different. So you said subtract 4, then complete the square. Are you sure about that, though? Oh, I see what you did. Huh. If I make it equal to 0, I'm going to say x squared minus 16 equals 0. I don't know why it keeps doing this stuff. Oh my goodness. X squared minus 16 equals 0. But, and you said complete the square, but then again, if I do that, I mean, honestly, this is gonna be plus 16, plus 16. We're gonna have x squared, plus bx plus c1 equals 16 plus c1. But then again, it just doesn't make sense in this situation. It is difficult. I mean, subtract 4 and then complete the square. But but the thing is, with the square, it's x plus 4 times x minus 4, though. If I factor x plus 4, x squared minus 16 equals 0, it's x. It's gonna be It's gonna be x plus 4 and x minus 4. The thing is, and so let me think here. Hold on. And we know that both of these were equal to 0. But also, we know that the range has, I'm sorry, the domain was -4 to infinity, so we're not even including form. And because it is, oh, I see. Because this equals 0, that means that the range has to be from 0 to infinity. I understand now. At least I think that's what it was, right? Was that correct? I think it was. Yeah, it is very complicated, guys. So what you have to do, and thank you, Lights, for letting me know this. You have to really think about what you're given. So we're given that the domain was from -4 to infinity. But the range, you have to kind of do the kind of the inverse in a way. But once you solve for once you solve for for y, you need to make it equal to 0, and then whatever x value you get, you need to then tie it back to the idea that the domain is from -4 to infinity. So whatever y value you get, you make it equal to, I guess. It is very complicated. It's going to be from 0 to infinity. You have to connect it to the idea of finding the roots. It is very hard, guys. This is very difficult. I just don't know the best way to explain it. Right, so I mean, they explained it in a similar way. I have seen it done in another way though, but it was the same way, but they were doing it more algebraically. But as you can see when you graph it, that's what it is. Now, graphing piecewise defined functions is another thing. The piecewise defined functions are functions where they have certain restrictions at certain endpoints or certain x values, kind of like the absolute value function had restrictions. We're going to do this one, and then finally that'll be the last example of this problem. Of this section. So it says sketch the graph of the function, and this is probably the only graphing example of this entire lecture, this entire section. So let me just type it. I'm just going to type it really quick. And I will do my best to explain this as best as I can. Hopefully I can explain it pretty well. So, this is example number, let's say it's example number, what is it? Hold on. 13. So we're just going right through this. I didn't do the other ones where it was about like stating it in terms of an application, because honestly, guys, I mean, you have to kind of understand how to, and I'm pretty sure I'm gonna go over how to evaluate these. I'm hoping they do this with in another section where they actually ask you to define the like at certain points. I'm gonna sketch the graph of the function, and then I'm gonna state the domain and range of this, because I know it doesn't say to do that, but I'm gonna do that for you guys so that y'all can see how this is done. So we have 3 things going on, and I'm just gonna state them very quickly. I'm actually gonna do it this way. And maybe, hold on, guys. I'm probably gonna do this. Hold on. Where is it? Like I said, guys, if you hear an airplane in the background, I apologize. I don't know why. I live next to an airport, like close to an airport, so not next to, but close to. So there's always stupid airplanes going. All right, so this is x squared such that I always put semicolons for this. X is less than or equal to 1. And then the next one would be, what is that? 3, such that, what was it? It was what? 1 is less than x. Is less than or equal to 2. How did I put this one? Hold on. Oh, okay. I'm sorry, guys. I'm sorry, guys. Hold on. I apologize. I don't know why. Oops. One is less than x is less than, what was it? X is less than or equal to 2. And then the next one is x such that x is greater than 2. Oops. Alright, this is the last one we're gonna do, guys. At long last. So let me think about this. I'm gonna go from -5 to 5. I don't think I'm gonna have to go that far. I'm gonna go from -5 to 5 on the x and y axis. Again, it really doesn't matter how you do your graph. If they don't give you a graph to do it with, just do your own graph, but just make sure you put enough endpoints so that the function is defined, like, or you can also make a table, but then again, I mean, I don't usually do that. So here's how we're gonna do this one, guys, and this is gonna be the last one that we do. I'm hoping that in the next section we get to actually define, we actually get to evaluate piecewise functions at certain x values, because it is not in this section for some reason. So I'm gonna do -5, -3, -2. Oops. Come on, come on. Oh dear God. I don't understand why it always does this. It's so annoying. Goodness gracious. Oh no, okay, we're gonna have to go lower than this. I'm sorry guys, hold on. I'm gonna just do it this way. 5, 4, 3, 2, 1. One, 2, 3, 4, 5. And then -1, -2. If it'll erase, -1, -2, -3, -4, -5. Same thing for down here, -1, -2, -3, -4, -5. Okay, I'm gonna zoom out here. We're obviously not going to define it for all of these x values, but I wanted to make sure I put enough. I want to have enough like points for each of these. Now let's look at the first restriction here for this function, this piecewise function. We have x squared such that x is less than or equal to 1. So what that means is, for the first function, I know that I am going to go from 1 to the left, okay? So it's going to be from 1 to the left for the first function, meaning it's like the function of x squared, but it's only to the left of 1. So if you think about it, I know that f of 1 will be defined for the first parts, for the first algebraic function, or the first piece of the function, which is x squared. F of 1, when it comes to this function, is 1 squared, which is 1. And I know that for every point to the left of that, it is going to be kind of like a parabola. So if I do 0 squared, it's going to be at 0. Wait. Oh, okay, yeah. It's going to be, so at 0 squared, it's 0. At -1 squared, it's 1. At -2 squared, it's 4. So what this means, guys, again, is that we're going to the left of 1 for this first part of x squared. So that's what it means. It's for all the numbers that are less than or equal to 1. And we're putting in a closed dot there because obviously that's where it would be. So we're going to do at -2 squared, it's going to be 4. And then obviously we can't go any higher than that. So we're just going to go ahead and, you know, kind of trace a parabola from front to the left of 1. You have to be careful with how you do these. You have to kind of also understand the kind of function you're dealing with a piecewise. So for example, in the very top part, we were dealing with a quadratic function, but it has a restriction. It's gonna look like the original parent quadratic function, but for all the numbers to the left of 1. That's why I started evaluating at 0, at -1, at -2, so on and so forth. That saves you a lot of time versus you actually drawing the graph of x squared and then erasing. I don't know. I don't like doing it like that because God forbid you'd use pen and you can't erase it. So yeah. Now the second one is f of x equals 3 from 1 to 2, but at x equals 1 it is not included. So at 3 we know that it is a constant function, but where it is not defined for x equals 1, so it's going to be an open circle at 1 comma 3, and then it's going to be a horizontal line from there, and it was from 1 to 2, so really it's going to look like this. Something like this. And actually, never mind. It's gonna be, I'm gonna do, I'll use the ruler here. I'm so sorry guys for the technical difficulties. I don't know why. It hardly acts like this. I don't know. I guess it's because I'm live. But this is what it would look like for the second restriction from 1 to 2. And yes, I know it looks very small, but that is how it would look for that. And then it would be x such that x is greater than 2. So again, if you think about it, for y equals x, so I'm going to do that yet in another color. I'm going to do it in this color. So y equals x such that x is greater than 2. So I know that it is not going to be defined at 2. I know that when y equals x at x equals 2, y equals 2. So I know that for that part, it's going to be the following way. So it's going to be, it's going to go, I believe, hold on. I believe it's going to go like this. So it's going to go something like this, an open circle at 2. And because we're heading upwards, because y is equal to x, we're doing the slope of 2. I'm sorry, the slope of 1. So 1, 1, so it's going to be right here. And it's going to be defined for all these other ones. And so on and so forth. And so that is how we graph this piecewise function. You just have to be very careful with the restrictions they give you. These are very tricky to graph. It takes a little bit of thinking. Oh God. I do believe that's how you graph it. Let me just make sure. Okay. Yes, that is how we graph it. So that is going to be it for this live stream, guys. I know it kind of looks right here. It doesn't matter if you put points or not. I mean, this doesn't have points, obviously, but I plotted every point. It doesn't have to have all points plotted, but that's how we do it when we graph them, because, I mean, honestly, we just, you know, we want to be as exact as possible when we're graphing functions. But that is going to be it for this live stream, guys. I am so sorry for the amount of difficulty with this with my Surface. I don't know why my OneNote kept freezing, but I do appreciate anybody that subscribes, and also I hope this helps a lot. I wasn't gonna make any more live streams, but I might just do them every Saturday or every weekend, depending on what day. But with that being said, guys, thank you so much for watching. And like I said, if anybody can subscribe, please do subscribe. And please like, comment, and or subscribe again. And I will see y'all next time. Bye, guys.